Hello everyone and welcome to another lesson. Today we will be looking at chapter 3, which focuses upon numerical descriptive measures. So the learning objectives for this particular chapter, we will be looking at three important concepts. We will be looking at the central tendency, variation and shape in numerical data. So we talked about types of data, two types of data, categorical data and numerical data. So from chapter 3 onwards, in this particular chapter specifically, we will be looking at numerical data, and we will be looking at properties of numerical data such as central tendency, variation and shape. We will also calculate descriptive summary measures for population, construct and interpret a box plot, calculate the covariance and the coefficient of correlation. So if you remember DCOVA from our previous lesson, I told you that in chapter 1, we looked at defining variables. Then in chapter 2, we looked at collecting, organizing, and visualizing data. From chapter 3 onwards, we will be analyzing this data. So before we move on, I need to give you a quick summary definition. So when I say central tendency values, we look at the extent to which all the data values group around a typical or central value. That is the key word here, central value. That is what when we say central tendency, that's what you have to remember. And when you talk about variation, you're looking at the dispersion or the scattering of the values, the dispersion. And when you say shape, that is simply the pattern of the distribution. Right. So in today's lesson, I have made it into 4 sections, right? So we will be talking about measures of central tendency. That's our first section. Measures of variation. That is our second section. Shape of distribution. And finally, numerical descriptive measures for population. So first, let's have a look at measures of central tendency. The first measure of central tendency we will be looking at is the mean. So the mean is very simple. It is where you take all the values and you sum it up and you simply divide it by the number of values that you have. But something you have to notice, you have to keep this in mind, although this is very obvious. Mean or the arithmetic mean is affected by extreme values. We call these outliers.
So what do I mean by telling this mean? What do I mean by this? Well, if you take few numbers, say x1, x2, x3, likewise, say you take n numbers. So when you say to calculate the mean, you're simply calculating x bar, which is x1 plus x2 plus likewise up to xn. You add up all the numbers and you simply divide it by the number of values you have, which in this case is n. This is, in order to shorten this, we use the sigma notation and we say you add up xi, where I is a subscript. I goes from 1 to n divided by n. So this is what we get as the mean, or in layman terms we call this the average. And in this case you have the xi means the ith value of x, and here you have the x bar, which is the mean, and you have the sample size n.
So this is the equation for the mean. The second measure of central tendency is the median. The median is simply the middle number or the middle valued number, which gives you 50% of the observations above and 50% of the observations below. So first, in order to calculate the mean, you need to calculate the location of the median. Before we do that, it is very important that when you're given a data set, that you arrange it from smallest to largest. This was mentioned in the last lesson as well. And then you simply calculate the median position. How do you do that? You take the number of values, you add 1 to it, divide it by 2, and that gives you the median position. And that position's number, the actual value, would give you the median. So when it comes to calculating the median position, if you have odd number of values, right, odd number of values, the median is the middle number. But if you have even number of values, say you have 10 values, then when you're calculating the median position, you take 10 plus 1 divided by 2, it's 11 divided by 2, 5.5 position, which means you take the fifth number and the sixth number and take the average. That is what is mentioned here.
So when you say the median, calculate the median, you're simply saying to calculate the middle number such that there are 50% above that number, there are 50% of the observations above that number, and 50% of the observations are below that number. So when you say to calculate the median position, right, so let's take a few numbers that were presented to you. So let's take 11, 12, 13, 14 and 15. These are your data values. Now how do you calculate the median? Very simple. First you calculate the median position. Calculate the median position. How is that done? You take the number of values you have, 1, 2, 3, 4, 5, you add 1 to it and you divide it by 2. So you get here 6 divided by 2 is 3. So that means you get the third positioning number. You have to consider the third position, which means the median value is 1, 2, 3 is 13. This here we first calculate the median position. Then only we calculate the median. That is very important to note. Now, if you consider another number range, say 11, 12, 13, 14 and 20. This was also presented to you. Okay, now how do you calculate the median? First you calculate the median position. Again, there are only 5 numbers here, so you add 1 to that, divide it by 2, you get the third position. So your median is 13. Now notice that in this data value series, the last value was 15. Here the last value was 20. So it's obviously different. However, this shows that the median is not affected by extreme values or outliers.
And the third measure of central tendency is the mode. Mode is simply the value that occurs most often. So what is important here to remember is the mode is not affected by extreme values. Now the mode there can be several modes, right? Or there can be an occasion where there is no mode as well. So an example is given here. So here, if you take the numbers, there is 1, 1, 1, 3, 2 5s, 1 7, 3 9s, 1 10, 2 12s, 1 3 and 1 13 and 1 14. So the mode is the value that occurs most often, which is 9. Why is that? Because there are 3 9s here, right? However, in this case, in this example, if you notice here, there are exactly only one value of each number. There is 1 0, 1 1, 1 2, 1 3, 1 5 and 1 6. So there is no mode in this data set. Right, now we talked about the mean, we talked about the median, we talked about the mode. What do we use? Well, it all comes down to the answer, it depends. Because the mean is generally used, but if you have extreme values, or in other words, outliers, then if you actually use this mean, when I say mean in this sense, I'm talking about the arithmetic mean, because you add up all the numbers and you take the average, then there is an issue. Then the median, of course, is not sensitive to these extreme values. So that is also a good measure. So that is why it said here, the last bullet point, in some situations, it actually makes sense to report both the mean and the median. And then there's another measure when it comes to central tendency. Now we talked about this mean. We talked about specifically the arithmetic mean, where you take the values, you add it up, and you divide it by the number of values data sets that you have, the number of data points that you have. Here we are talking about something called the geometric mean, right? The geometric mean. Now, what is this? How does this differ from the arithmetic mean? Simply, you take the data set, you take the data values, and you multiply these data values, and you take the nth root. If there are n data sets, you take the nth root of this value. So assume that you have 10 data points, you multiply all those data points and you take the 10th root. Assume you have 15 data points, you multiply all 15 and you take the 15th root. That gives you the geometric mean. From this, they have derived this concept known as geometric mean rate of return, right? Where is this used? It measures the status of an investment over time, right? So this you will be using in your next semesters, right? Especially the ones who will be specializing in, if you are doing financial analytics, you will need this area. Right, so how do we calculate this geometric mean? Very simple. Similar to this idea, you take the rates, right? So assume there are n number of rates, 1, 2, up to n. You add 1 plus r1 times 1 plus r2 times up to 1 plus rn. You take the nth root, right? And you deduct 1 in order to get the percentage value. So if we were to look at this particular example, so you're told here an investment of 100,000 declined to 50,000 at the end of year 1 and rebounded to 100,000 at the end of year 2.
So when we are looking at this particular example given to us, it says an investment of 100,000 declined to 50,000 at the end of year 1 and rebounded to 100,000 at the end of year 2. So at the end of year 1, let's say take it as x1, at the end of year 1 you have 100,000. And then at the end of year 2, let's take it as x2, you have 50,000. And at the end of year 3, let's take it as x3, you have again 100,000. Right. Now notice here, from at the end of year 1 to the end of year 2, there's a 50% decrease. From end of year 2 to end of year 3, there's a 100% increase, right? So initially there's a 50% decrease and then there's a 100% increase. So in total, if you notice, from start to end, there is actually no change. You started with 100,000 and you ended up with 100,000. So your overall 2-year return is actually 0. But if you were to calculate the arithmetic mean, what would you do? You would take the average of these percentages, which is negative 0.5. Why is it negative? Because it's decreasing. Why is it 0.5? Because you're taking 50%, plus 1. Why is it 1? Because there's a 100% increase, and you take the average, divide it by 2, and you get 25%. This number here tells you from start to end, there's a 25% increase, which is actually not true. But if we were to calculate the geometric mean, how would we go about this? Well, you would take 1 plus negative 0.5 times 1 plus 1, and you take the square root of this, because there are only two numbers, minus 1 in order to take the percentage value. Here you would get, once you solve this, you would get 0.5 into 2, and you take the square root of that, minus 1, and you get 0. So this value actually represents what has happened here. Rather than the arithmetic mean value, the geometric mean value gives you a better representation.
So, like I mentioned, there's a 50% decrease and a 100% increase here. Overall, there is actually no return. There is zero return. So this was the calculation that we did, right? So here you have a misleading result when you calculate the arithmetic mean. When you calculate the geometric mean, that actually gives you a more representative result. So in summary, what did we talk about under central tendency? So we talked about the arithmetic mean. We talked about the median, which is the middle value. In an ordered array, that is very important to keep in mind. When you're given the data set, you have to order it from smallest to largest. Then you have something called the mode, which is the most frequently observed value. And we did something called the geometric mean, which is the rate of change of a variable over time. And we use this mainly for the rate of returns. So that is it for measures of central tendency. We talked about arithmetic mean, median, mode, and geometric mean. Now let's talk about measures of variation in the next section. So here we will be talking about four concepts under variation, measures of variation. We'll be talking about what is range, variance, standard deviation, and coefficient of variation. So measures of variation actually gives you information about the spread or dispersion of the data values. So the first measure of variation is the range. This is a very simple concept, because when you're given the data set, you first order the data set from smallest to largest. The range is simply the difference between the largest value and the smallest value. That gives you the range. For example, in this example, when you order the data set, you will see the largest value is 13, the smallest value is 1, the range is 13 minus 1 is 12. But if you notice, there's a small problem, because the range can be misleading. Why is that? Because the range actually ignores the way in which data are distributed. So if you notice in the previous slide, you don't actually consider the distribution here, right? So there are 3 8s, there are 2 4s, there are 2 11s, but the range does not incorporate all of that into this value, right? So that is why we say that it's misleading. It ignores the way in which data are distributed. And it is also sensitive to outliers, right? Because now assume you have this data set, and then you have another one data point, which is 100. So then your range would be 100 minus 1, which is 99. That tells you, okay, for a reader or an observer who sees this range, he sees that the range is 99. So he thinks the values are really spread out. But actually what's happening is the values are in between 1 and 13, and there's one outlier data point, which is 100. So that is why we say it's misleading. A second reason, sensitive to outliers. Right, so we talked about the range, which was the first measure of variation. The second measure of variation is the sample variance, right? So all of these things that we're talking about, we are talking about sample. We will come to population in the fourth section. The first three sections, which is measures of central tendency, measure of variation, and the shape of distribution, we are talking about samples. So under measures of variation, the second measure of variation is the sample variance, which is simply the average of square deviation of values from the mean. So what do I mean by this? Sample variance is given by this equation. And if you notice, you take the value, the ith value here, and you deduct the average value of those data points, right? And then you divide it by n minus 1. I have made a small mistake here, which is actually very critical. You have to take the square deviation. So actually, there should be a 2 here, right? Because you're taking the square. There should be to the power 2. Xi minus x bar squared, and you take the addition divided by n minus 1. This is also an important observation, because when you're calculating the sample variance, you divide it by n minus 1. So the third measure of variation is the sample standard deviation. Very simple. You calculate the variance and you take the square root. Now here I have included that square, so you don't have to worry, right? This was what was missing in the previous slide. So what did I do? You simply calculate the variance and you take the square root of it. So these are the steps of calculating the standard deviation. Let's have a look at an example.
Okay, now let's take a example sample data set and let's see how we calculate this standard deviation. So let's take the sample data set as 10, 12, 14, 15, 17, 18, 18 and 24. This is our sample data set. Quickly you notice and you count the number of values you have, you will see that there are 8. And you also calculate the mean here, the arithmetic mean, and you will get 16. Right, so how do we go about calculating the standard deviation, the sample standard deviation? You take the value, deduct the mean, and you square it. Plus, you take the second value, deduct the mean, you square it. You go on in this fashion, right, up till the last element 24 minus the mean 16, square it, and you divide it by the number of values minus 1, 8 minus 1, and then you take the square root of this whole thing. When you calculate this, you will come across the value 4.3095. What this tells you, this value tells you, it is a measure of the average scatter around the mean. So this is the average scatter around the mean. That's what this number tells you. So how do we calculate the sample standard deviation using the calculator? Here I have the Casio FX9991EX, right? So on this calculator, first you click on the menu setup, and here you will see number 6 gives you statistics. So you click on 6, and you're considering only one variable, so you click on 1, and then you enter the data. So you have 10, and then you press on equal. That inputs the data 12 equal 14, 15, 17, 18, and you have another 18, and then finally 24. Right, then you click on AC. So that inputs the whole data series into this calculator. Then you simply press on this OPTN option value, and you click on that button, and you then click on the second one. That's what you want, one variable calculation. So you click on 2, and you get all the values that you need, the average, the sigma x squared, then variation, this is your population variation, this is your sample variation. What do we need? We need the sample standard deviation. You press the down arrow key and you get the sample standard deviation. This is the same value that we got previously.
So this was the example I talked about, right? So you had the data set and there are 8 data points. You had the average of 16 and you calculate the sample standard deviation. You got 4.3095. How do we calculate this using the calculator? Right. Now, when it comes to comparing standard deviations, right? So let's take a look at this data set. So here the average value is 15.5 and the sample standard deviation is 3.338. And you have another data set. Here also the average is 15.5, but the sample standard deviation is 0.926. So see, for data set A, the sample standard deviation is actually higher than data set B, which means data set B is actually clustered together relative to data set A. And data set C is actually very much spread out, hence why you have a very high sample standard deviation. Now, in all of these data sets, the average value or the arithmetic mean is 15.5. The only difference is the change in the sample standard deviation. So what I was trying to tell you in the previous slide was, the smaller the standard deviation, this is what your values would look like. It would be clustered together. But if you have a larger standard deviation, your values would be more spread out. So let's have a small summary up to what we did. We actually talked about range, variance, and standard deviation. So if your data is actually spread out, right? If your data is spread out, then you have a greater range, variance, and standard deviation. And if your data is actually concentrated, you have a smaller range, variance, and standard deviation. And if all the values are the same, that means there's no variation. Then all these measures, that is range, variance, standard deviation, will all be 0. Important to keep in mind, although it's again very obvious, none of these measures are ever negative. So none of these measures are negative. That's important to keep in mind. The fourth measure of variation that we are going to look at is called the coefficient of variation. What does this do? This measures the relative variation. What do I mean relative variation? Shows the variation relative to the mean. That means you calculate the standard deviation and you calculate the coefficient of variation gives you the standard deviation relative to the mean value. Let's have a look at an example.
So let's consider an example for coefficient of variation. Before we do so, let's write down the equation for coefficient of variation. I will call this CV in short, and that is given by the sample standard deviation divided by the sample mean into 100%. Right, so let's take an example of two stocks. Let's name them stock A and stock B. So we have two stocks and you're given the average price of stock A for last year as $50, and for stock B your average price for last year is given by $100, like so. And also for stock A you're given the standard deviation, which is $5, and for stock B the standard deviation is also $5. So the standard deviations are the same. Now if we were to calculate the coefficient of variation for stock A, what would you do? You take the standard deviation 5 divided by average price for that year 50, multiplied by 100 because you're considering the percentage amount. Here you will get 10%. But if you were to calculate the coefficient of variation for B, you take the standard deviation 5 divided by the average price, which is 100, and you take the percentage value of that, you would get 5%. Now notice the two values. Both stocks have the same standard deviation that we noticed. However, stock B is actually less, there is less variation in stock B relative to its average price compared to stock A. Because if you take the variation in stock B relative to its average price, it's only 5%. But for stock K, the variation is higher relative to its average price and it's 10%.
So this was the example we talked about, right? So if you notice, for stock K, the coefficient of variation is 10%. For stock B, the coefficient of variation is 5%. Both stocks actually have the same standard deviation, but when you consider stock B, the variation is actually less relative to its price compared to stock A. Right. We will also look at something important that you all know since you come after A-levels or the advanced level examination, where you calculate the Z score. So why do we calculate this? This is a way of actually locating an extreme outlier. So what happens here? To compute the Z score of a particular data value, you subtract the mean from that data value and you divide it by the standard deviation. The Z score is the number of standard deviations a data value is from the mean. So that is how you would interpret the Z score. It is the number of standard deviations a data value is from the mean. Right. So if your Z score is less than -3 or greater than +3, you would consider that data value as an extreme value. The larger the absolute value of the Z score, the further the data value is from the mean, right? So how do you calculate the Z score of a particular data point? Simply take the data point, subtract the average or the mean value of that data set, and you divide it by the sample standard deviation of the data set. So if you consider this particular example, suppose the math SAT score is 490 with a standard deviation of 100. So if you're asked to calculate the Z score for a test score of 620. So you take the 620 data point, deduct the average score or the mean value, which is 490, and you divide it by 100. You get 1.3 as your Z score. How do you interpret this? Very simple. A score of 620 is 1.3 standard deviations above the mean and would not be considered an outlier. So what is this 1.3? It tells you that your score of 620 is actually 1.3 standard deviations above the mean because it's positive. If it was negative, it would be below the mean. Right. Next up, we have shape of a distribution. Now, in order to look at the shape of a distribution, we would be looking at the skewness and the kurtosis. What is the skewness? It measures the amount of asymmetry in a distribution. What is kurtosis? It measures the relative concentration of values in the center of a distribution as compared with the tails. So skewness describes the amount of asymmetry in the distribution. What do I mean by this? So left skewed would look something like this, where your tail is actually longer. Right skewed is where your right hand side tail is longer. And symmetric is, well, it represents the symmetry, right? So in the left skewed, you have the mean is actually less than the median. When it's right skewed, your median is less than the mean. So your skewness statistic, if it's left skewed, you would get negative values. If it's right skewed, you would get positive values. And if your skewness statistic is 0, it's telling you that your data set is symmetric. When it comes to kurtosis, it tells you the relative concentration of values in the center as compared to the tails. What does that mean? Something like this. So if your kurtosis statistic is negative, it tells you that your relative concentration of values in the center are actually more spread out. But if your kurtosis statistic is positive, that tells you that the relative concentration of values in the center are very high compared to the tails. Right, another measure of shape of a distribution. So we talked about kurtosis and skewness mainly, but we can also talk about this concept known as quartile measures, where you segment your data set into 4 quartiles like this. So 25% would be below your first quartile, 25% would be between your first and second quartile, likewise 25% between Q2 and Q3, and 25% of your data sets above Q3, right? So here Q2 actually means, because if you notice Q2, if you calculate Q2, you have 50% of the data below Q2 and 50% of the data above Q2, which tells you that Q2 is the same as your median. So in this section, how do we calculate Q1, Q2, Q3? First, you calculate the positioning of Q1, Q2, Q3. How do you calculate the position? You take the number of data points that you have in, or the observed values, you add 1 and you divide it by 4. Why do I divide it by 4? Because I have segmented my data set into 4 sections. So your second quartile position is calculated by, you take the number of observed values, add 1, you divide it by 4 and you multiply it by 2. That's how you get this. Your third quartile position is calculated by n plus 1 divided by 4 multiplied by 3. So let's have a look at an example, but before that, let's have a look at the rules, the calculation rules. So when calculating the ranked position, we have to use the following rules. If the result is a whole number, it is the ranked position to use. If the result is a fractional half, like 2.5, 7.5, then you average the two corresponding data values. If the result is not a whole number or a fractional half, then you round the result to the nearest integer to find the ranked position. Right, so you take a data set and let's have a look at this particular example.
So let's take a example data set and see how we calculate Q1, Q2 and Q3. So let's consider the data set where you have 11, 12, 13, 16, 16, 17, 18, 21 and 22. Here you notice that there are 9 numbers, so you write it down. And now how do you calculate Q1? That's what we need. First we need to calculate the positioning of Q1. So that's what we do first. Q1 position. How do you do that? You know that there are 9 numbers. You add 1 to it and you divide it by 4. So then you get 2.5. This is not a value, this is the position, 2.5 position. So then, in order to calculate Q1, what would you do? You take the 2.5th position, meaning you take the second number and you take the third number, you add the 2 and you take the average. So the second number is 12, the third number is 13, you add the 2 and you take the average and you get 12.5. 12.5 is your Q1. Similarly, you can calculate Q3. I will leave Q2 to you. Q3, first you calculate the Q3th position. How do you do that? You take the number of values you have, 9 plus 1 divided by 4 times 3. then you get 7.5. This is not a value, this is the position, right? 7.5th position. So you see which numbers are your 7th and your 8th, and you take the average of those two. So 1, 2, 3, 4, 5, 6, 7. So 18 plus 21 divided by 2 would give you your Q3. 18 plus 21 divided by 2, 19.5. And this is your Q3.
So this is what we did. We took the data set, we calculated the Q1th position as 2.5. So we said that you take the average of the second and the third value, you get 12.5, and likewise you calculated Q2 and Q3. The interquartile range is very simple. It's a very simple concept. It's simply where you take the difference between your Q3 and your Q1. Something that I missed here that is very important, the interquartile range not influenced by outliers. So Q1, Q3 and IQR are not influenced by outliers. That is something important to keep in mind. So this is an example. You have your data set, right? And you have calculated the minimum value, which is 12. Your maximum is 70. Your first Q1 or your first quartile value is 30. Q2 is 45. Q3 is 57. And when you calculate these values, you will notice that 25% of your data is between your minimum X value or your data point and your Q1. Similarly, you will find 50% of your data in between Q1 and Q3. So the difference between Q1 and Q3, that is 57 minus 30, gives you the interquartile range, which is 27. So based on this, we have this concept known as 5-number summary. So if you are given a data set and you're asked to calculate the 5-number summary, what do? You calculate these 5 values. What is your smallest data point? What is your largest data point? You calculate your Q1, Q2, and Q3. So why do we calculate this? Because you need to get an understanding of your distribution shape. So once you calculate the 5-number summary, you can actually identify whether the data set is left skewed, symmetric, or right skewed. You can refer to this table and then you will understand which skewness is the distribution inclined towards. Then we have this concept known as box plot. It is a graphical display of the database on the 5-number summary. It's a graphical display of the data based on the 5-number summary that we calculated. So from this source, you can get an idea about the skewness of the data set. So for example, if your box plot is, the tail of your box plot is longer, you know it's left skewed. If your right tail of the box plot is longer, you know it's right skewed. And if it's symmetric, if the box plot looks symmetric, you know that the data set is also symmetric. So in this case, in this particular example, this data set 0, 2, 2, 3, 4, 5, 5, 9, 27. When you construct the box plot, you will see that the data is actually right skewed because this right tail is very long. It's longer than the left tail. And finally, we have numerical descriptive measures for a population. So earlier we talked about a sample. So we were talking about the sample statistics. Now we are talking about the population. So we will be talking about the corresponding parameters. So we'll be talking about the mean and the variance. So here, if you note this particular symbol, this tells you the population mean. For sample mean, you have X bar. If you have this symbol, this is sigma squared, that tells you the population variance. If you have S squared, that tells you the sample variance. So the mean is actually, population mean is very much similar to how you calculated the sample mean. What is important is actually the population's variation, because that differs from your sample variation, because in your population variance you divide by the population size, but in your sample variance you actually divided it by sample size simple n minus 1. In your population variance, you divide it by the population size. In your sample variance, you divide it by the sample size minus 1. That is an important observation to keep in mind. Then we also have something called this empirical rule. What does this tell you? This actually tells you again about the distribution. So what this tells you is approximately 68% of the data is in a bell-shaped distribution. That is the condition. So if you have a bell-shaped distribution, which means your distribution is symmetric, that will tell you that 68% of your data is within one standard deviation of the mean. So if you have a bell-shaped distribution, 68% of your data would be within one standard deviation of the mean. So if you again have a bell-shaped distribution, 95% of your data would be within two standard deviations of the mean. That's what I've told here, two standard deviations of the mean. If you have 95% of your data, 99.7% of your data would lie within three standard deviations of the mean. And then you have something called the Chebyshev rule. Now the empirical rule only applied to data sets which have a distribution of a symmetric distribution or a bell-shaped curve. And the Chebyshev rule is actually a more generalized rule than the empirical rule, because it does not take into consideration the distribution, regardless how the data are distributed, right? So how do you calculate it? It's 1 minus 1 over simple k squared times 100% of the values will fall within k standard deviations of the mean. You have to keep in mind that simple k is greater than 1. So what do I mean by this? You take an example, right? Something like this. I would recommend to you, if you want to learn more about this Chebyshev rule, please refer to the reference book that I mentioned in the first video, and you will find many examples and a better explanation to this Chebyshev rule. And then you have something called the covariance. The covariance is actually measures the strength of the linear relationship between two numerical variables. Up to now, we've been talking about only actually one variable or one data set. So if you have two data sets, if you want to measure the strength of the linear relationship between the two data sets, we calculate the covariance. So how do you calculate the sample covariance? By this particular equation. You take the first data set and you calculate the difference between the data point and the average values of that first data set. And then you multiply that by the second data set's point minus its average value, and you take the summation and you divide it by the sample size minus 1. Of course, in this case, if you notice, both data sets have the same sample size, which is simple n. Now, we have to keep in mind the covariance is only concerned with the strength of the relationship, right? It only concerned with the strength. There is no causal effect. So one does not imply the other. That you cannot say. You're only talking about the strength. So one of the disadvantages which I've mentioned here is that it is not possible to determine the relative strength of the relationship from the size of the covariance, right? So how do we calculate this relative strength? We use this coefficient of correlation, right? That measures the relative strength of the linear relationship between two numerical variables. Now, in the previous slide, if you notice, if we get a positive value for covariance, that tells us x and y actually are moving together in the same direction. If you get a negative value, you can say that x and y are moving in the opposite directions. If x and y, if you get covariance 0, it tells you x and y are independent. But this doesn't tell us the relative strength between the two, right? So how much is X dependent on Y, or how much is Y depending on X, by how much, that is not told. That is told by this concept known as coefficient of correlation. How do we calculate that? Very simple. You calculate the covariance first, coefficient of covariance first, which is what we did before, right? The covariance. The covariance between X and Y is calculated, and then you divide that value by the sample standard deviation of X times the sample standard deviation of Y. This gives you the coefficient of correlation. Now, what are the features of this coefficient of correlation? Right? It ranges between -1 and 1. The closer it is to -1, you can say it has a strong negative linear relationship. The closer it is to +1, you can say there's a strong positive linear relationship. If it's close to 0, you can say that there's a weak linear relationship. So an example would look like something like this. So if your coefficient of correlation is exactly -1, you can say there's a negative relationship between Y and X. If your coefficient of correlation is +1, you can say that there's a positive relationship, positive linear relationship between Y and X. But if your coefficient of correlation is closer to 0, something like +0.3, there seems to be a positive trend, but it's more scattered around, right? And if it's exactly 0, Y and X are actually not related. There is actually no linear relationship. So that is it for today. So we talked about a lot of things. We talked about central tendency. We talked about measures of variation. We talked about the distribution, the 5-number summary. We also talked about covariance and correlation coefficient, right? We talked about a lot of things in this particular chapter. All these things are very important, and I hope that you would go through this video again and try and understand this particular chapter. That is it for today. Thank you very much, and I hope you have a productive day.